from your thesis that you are doing your seminar.
Yes,
Okay. Okay. Go ahead.
Yeah, go ahead. Okay. This time in my defense, there's no formula thing. There's no formula in my defense. Now, in this report, all of formulas is about the methodology, the mechanics, the mechanism. Now, let's go. Yes. First, I think we do carbon sequestration because the global warming, and the driving power, the reason of global warming is the ever increasing carbon emissions, and therefore, in order to stop the trend of global warming, which negative, we should reduce our carbon emissions, and a good method approach to the carbon emissions is geological carbon sequestrations, and geological carbon sequestration is the topic of this report. And here we will focus on the mechanism, the mechanism in the geological carbon sequestration. So first, this model. When we inject CO2 in the underground, it will override the brine, and the CO2 can dissolve into the brine. And when CO2 dissolves into the brine, the pH will reduce, and with the pH reduced, we have higher hydrogen concentration, and the rock will dissolve, and the rock will dissolve. So this is the system. This is the system we are going to study. Actually, we can add as many reactions as you wish if you want. But here, because these reactions are the most important these reactions are the most important reactions during the geological carbon sequestration. That's the reason we only put these reactions. Even though it's still a lot of reactions, a lot of species, so it's very complex. And let's see. So first, reaction. In this reaction, first, which split the reaction into kinetic reaction and equilibrium reaction. For instance, we have one kinetic reaction. The dissolution of calcite is a kinetic, and the rest equations, the reactions are equilibrium. People may ask, why do we split the reactions into kinetic reaction and equilibrium reaction? Why don't we treat all of them as a kinetic reaction? This is because why do we treat some reaction as equilibrium reaction? Because the reaction is very fast. If we treat these very fast reactions as a kinetic reaction, the reaction rate will be very high. So the reaction time is very short. Therefore, in the simulations, we should use a very small time step to solve the reaction. If we use a very small time step, it might take a very long time. We need a lot of simulation time steps to simulate a long time scale. For instance, the reaction time of this CO2 dissolution may be 1 second, one minute, but we are going to simulate 1,000 years. So if we treat them as a kinetic reaction, maybe we will simulate very slow. So that's the reason we first split the reactions into kinetic and equilibrium. And if we split the reactions into kinetic and equilibrium reaction, we will have some interesting things. We have like a kinetic species. The kinetic species only participate in the kinetic reaction. For instance, the calcite does not participate in the other equilibrium reaction. So this kinetic species, we will call this species, we will call it a kinetic species. And now actually our reaction system can be simplified with this very short form. And the new is the stoichiometric matrix, and they are like a kinetic one, equilibrium. And we have for the kinetic reaction, we have the rate law for the kinetic reaction. We can solve this reaction rate very easily, explicitly. But for this one, we just put it here, but we have no solution for equilibrium reaction rate. But later, we will remove this because we do not need this. They are infinite, we do not know, but we do not need this. Now, yes. Now, for solving the kinetic reaction, this is the reaction system in the last slide. Now, for the kinetic species, we have this rate law. The time development of the kinetic species is controlled by the reaction rate and the stoichiometric matrix. And this term is just to transfer the unit of reaction just to change the unit, because when we solve the chemical reaction system, we usually use the molar, the unit of chemical reaction is usually in molar, but in our transport system, we usually use the kilogram. So this is like the molecular weight. So with this matrix, we transfer the reaction rate, the mass change rate into the molar change into the kilogram per second. And so if we have NK kinetic reactions, so we have NK kinetic, we have NK equations for this form. And similarly, if we have NE equilibrium reactions, so we will have NE equilibrium equations. And this is, I'm not sure if all of you know this form. This equation is a mass action law, and this is activity. Actually, we can treat activity. We can treat that activity is the concentration. Activity. Sometimes we think we can assume the activity is equivalent to the concentration, and this is the equilibrium constant. Each reaction has an equilibrium constant, and we can find this equilibrium constant from the database. I think if you search equilibrium constant something in Google, and they will tell you you will find equilibrium constant for every reactions. So now we have NK equations for kinetic reactions, and we also have NE equations for the equilibrium reaction. However, we may have many species, more than with the number of the species NS might be larger than the number of the equations. So we need more constraints. And here we use the conservative components as our the additional constraints. What is a conservative component? I will give you an example. For instance, when the liquid water evaporates into gaseous water or water vapor, when liquid water evaporates into gaseous water, and then the mass of the liquid water will reduce, and the mass of the water vapor will increase. But the sum of the water, of the liquid water and the gaseous water is unchanged. So we can call the sum of the liquid water and the gaseous water as the component and the similar and the component. So we define the component in this way. This is the kernel matrix, and the kernel matrix is only a function of is a constant. So as long as we know the reaction system, we know this reaction, and we know it's a component matrix. And the calculation of the component matrix will be given in subject. In these papers you can find. And now, so we have now we have the functions for the reactions and also the functions for the invariant conservative component. So now we have enough functions. We have all the functions we need. Now next step is to solve these functions. How to solve these functions? I think yes. This is the function. I think in the last step, we just put all these three in the matrix, and we have this function. We have this function system, and this system is we put in the Newton-Raphson form. We want to solve it with the Newton-Raphson method, and we move all these functions to y side, and we have this form. And we move here to the left, and we get this function, and this function we call, I think it's Newton, the Newton-Raphson form of this function. And to solve this, we need to get the Jacobian matrix of this function system. And the Jacobian matrix is a derivative of this system. And for instance, the derivative of the last, the mu e log a minus log k is given in here. Because log k is a constant, so the derivative is 0. And mu e is a constant, so the derivative is mu e, the log a over the partial derivative of log a over sheet. The sheet is the mass of the species, the mass. So we want to know this. So. And also, similar, if we do the derivative of this term, we will get u, and this is a constant. The mass of the component does not change over time, so this is 0. So similarly, we have these things. And if we get the Jacobian matrix, we can get the change of the mass of all the species, and we can update it based on the initial gas, and then we do like iteratively to solve this system, and we can get the species, the mass of all the species after when dirt sheet goes to almost 0, and this is how we solve the chemical reactions. In this, when we solve these chemical reactions, we do not consider the transport, so there is no transport. Now we go to transport. We first give this and then transport, and then the key is how to combine transport and reaction. We first split them and then we combine them. Now we go to transport. So I think everyone will know this. This is the transport of one species. This is the mass change of the species, and this is the adverbation term of this, the adverbation term, and this is the dispersion term, and this is the source term due to like injection, extraction, or some boundary conditions. And this term is the source term due to chemical reaction. I think this term, we do not like this term, not because it has a chemical reaction, because we do not know the equilibrium reaction rate. So if it is a kinetic reaction, it's fine. But if there is a if the reaction is a equilibrium reaction, the reaction rate is infinite. So we should move this term if we want to solve the transport system. So we will go. So because we knew, because the component is independent of reaction. So instead of solving the reactive transport of this the species, we can build equations based on the mass balance of the component. How to get the mass balance? How to get the mass balance equation of the component? So we multiply by the kernel matrix for each term. We multiply by the kernel matrix to each term, and we will because if we multiply this term to this, we will get this one becomes 0 because if we do this because this is 0, this is the kernel because if we multiply the kernel matrix to this here, we will get how say the component. We'll get a component. Yeah, we will get the component. The component is does not change. Is independent on the reaction rate. So now we have we have changed our reactive transport equation to purely transport equation. Now there's no reaction term at all in the equations. Now we should solve these equations. We need to solve these equations without reaction term. And moreover, because normally the number of the component is smaller than the number of the species, so we have also reduced the number of the functions. Now, for instance, here we have 9 species, so we have 9 equations, and now we have 4 or 5. We have 4 components, so we only have 4 transport equations without reaction. Now let's go to yeah. The overview of this the reactive transport system is the first is divided into two parts. The first part is the reaction, and the second part is the transport. Transport without reaction. The first is the reaction without transport. And now we will see how to solve this, how to couple or decouple these two parts. I think the most important thing is if we have a very complex system, the first important thing is we should know the independent variables. Once we know the independent variables, I think we can calculate all the other dependent variables. So if we know these things, we can solve all the other dependent variables. So, but still we still have a lot of things like independent variable. For instance, here we choose the liquid pressure, gas pressure, porosity, and the mass of kinetic species and the component. So we may have many components. So this term, this may have the independent of the number of the secondary or reaction independent variables may be very huge. So we will not solve x and y altogether. We want to solve them. We first solve the transport variables or transport independent variables, and then we solve the reaction independent variables. If we solve them together, the matrix will be very huge and it's difficult to control them. But if we split them, now things becomes clear. And so first we solve these three transport variables, transport independent variables. Let's see how to solve it. And we have 3 independent variables. So 3 independent variables, and we need 3 governing equations. We have 4 governing equations for the component, and we select 3. How to select here? Because I select the water, CO2, and the mineral component. I just 3 components. We have 3. For instance, we have 4 equations, but we select 3. the details how to select them is not discussed here, but we have 4, we can select 3. So we have 3 equations, we have three independent variables, we have 3 equations, and so we can solve them. And so this is the transport system now is very simple. You know, is the simple form of the transport program is the 3 transport equations based on 3 conservative components and 3 independent variables. And we want to solve these 3 independent variables by solving these 3 equations, and also in the same way we solve it with Newton method, and also similar the same we solve it we first got to get the Jacobian matrix of this function is in this way, and we get the dirt x, and then we update and we do this iteratively until this the dirt x goes to very small, and this is how we solve the transport the independent transport variable. So now we have this. We have, by solving this, we already get the PLPG. If we know the PLPG, PL, the liquid pressure, the gas pressure, then we can get the capillary pressure. Once we know the capillary pressure, we can know the saturation, we can know the relative permeability, and we can also get the Darcy flux of water discharge, of the gas discharge. We can know every flow information. So with these 3 independent variables, we can know every flow information. Now we know the flow information. Once we know the flow information, we can update the mass of the component or the concentration of the component, because this we solve this the advection diffusion of the components, the mass of the components. But because we already know the flow information as soon as we have the independent transport variables. So now we can easily update we can calculate the independent reaction variables. Once we have independent reaction variable, I'm not sure if this. So once we have these independent reaction variables, we can solve the reactions I showed in the very beginning. Once we know these things, we can solve the reaction, the chemical reaction. So now the summary of this reaction, the summary of the methodology is we first update the pressure, update the independent we first update the flow field, and then with the flow field we update the mass compositions by advection diffusion, and then finally we calculate the mass compositions of a local grid based on after the transport. So we first solve the transport, and then we solve the reaction. Now we will see the code. Oh, okay. We have uploaded the code to the GitHub, and you can go there and you can download. It has some examples for instance. All the examples are in this folder. You just go there and you can find the file you are interested. You can, for instance, this is a benchmark. We do simulation in a y-dimensional system, and we compare the numerical result with the theoretical result. It looks good. We can get the saturation of the gas saturation. This is when we inject gas in a y-dimensional like a bar. We inject gas, and this is a gas saturation distribution. And also we can know this term is the porosity chain. The porosity chain. This AS means the AS just denotes the reaction rate. If AS is high, the reaction rate is is very high, so the porosity change is huge, is not huge, but it's larger if the reaction rate is zero. So the porosity change is almost zero. So and also pH, because when you inject CO2, the pH will decrease. So this is the detailed discussion is not given here, but this is the qualitative result of the code. And also this is in the difference about this is the two-dimensional system. From here, I just want to show it's very easy to put this field in the code. You can easily define your grid system, and you can do whatever you want. This is just a two-dimensional example, and actually you can also do three-dimensional if you want, but here is a two-dimensional example. It's simple, and now let's go to the code. A short introduction to the MATLAB. This is not a MATLAB. This is an introduction to MATLAB. Yeah, this is introduction to MATLAB. Suppose nobody knows MATLAB, so I will start from zero. So in the grid, in the MATLAB, you can put many related stuff in one objective, I'm not sure, or in a structure. For instance, here G is the grid system. The grid system has many branches like cells, phases, and the grid dimension, and partition dimension maybe, and nodes. They have this kind of, if you enter G, the cell, you will know the cell's information. Now let's go to the cells. So you can have the cells. We will see, for instance, we can know the cell's volume. We use the number of cells is 500, so we have the volume, and the central is the center of the cells. So if you enter these cells, their central is, and you will know the center of all the cells, X, Y, Z directions. So this is the method of the data and the function. And most important, this is important because I think this is similar to every function, like maybe Python, Fortran, C++. I think they're the same because similarly, like here we cannot. If we do like a large numerical system, we have to use a function. We just to do this, we just define our function elsewhere. Anywhere we just define a function and we put it in a folder, and it will cite this function automatically. So it's not that complex. You do not need to say anything about how to cite it. You just define this function and you put it anywhere in your folder. And if you write this file, if we call this function, and it will go directly here. So it's quite simple to use MATLAB, and it's also very easy to modify. And yes, thank you. I'm sorry, I couldn't forget. So in the thing is like here the reaction and the transport we split, so you can easily modify the code if you want to do more complex reactions. You can modify it, and the structure of the code I think is simple. It's easy to understand the structure. Okay, thank you.
I would like to ask if in your code, you have to change something, the permeability, or maybe the grid. You actually change the
For the porosity, I define the division. I do not really change everything. I do not you change the grid. if you change the grade, I think,
if it's more larger grid, for instance, instead of 500.
yeah, it's simply just in the top, in the first file, the executive file, the first, the main file, you can define this one. In the main file, you can see the easy, you can see this is the porosity, and you just change it. It's like you define something.
Yeah, I suppose the same is permeability or other porosity or whatever.
Whatever, yeah, you always define this them into kind of define them into function. And you define the function and you cite like the relative permeability, the capillary pressure, you can define such function elsewhere and you cite them and you can use them.
But things like porosity are in this function.
No, porosity you can store them in here. Like here, this is you store them in a group like state variables. All the everything like the porosity, the concentration, the mass of all the species are stored in the state variables. Like we have like here is G value. We can use a state and state dot saturation, state dot pressure, state dot porosity. State everything is grouped in the.
So you have state variables.
Yeah.
But you also have, I think, permeability or saturated permeability, intrinsic permeability.
Maybe it's in rock, in other group like rock permeability, rock porosity, like different objective or different structures, like different like this. Here is the grid system. This state stores all the grid information, like the cells or grids, like the types here. Like the other for the state variables, you can state every state variable, like the pressure, and if temperature or everything, you can put in state variables. Also in this structure and in this structure.
Do you need some sort of? So you change it and then you run it. You don't have to make an executable or something.
No. It's just there's a file. You can see everything. You click. There's no.
Then you run it.
You can see everything. The data you input. It's not. It's like.
Okay, but just because I don't know MATLAB very well, so that trust me.
Okay, so you solve the transport variables, first pressure and velocity, then you solve the components, and then the kinetic
reaction.
Only the kinetic part.
The reaction part will be
My question is after you solve the components, you use this information for solving the kinetic reactions.
You use the information.
No. I think go to. You have a system where you solve the chemistry.
Chemistry.
This system. So this is the last part of the solving process.
This is the last part. Actually, it's inside. They are iterated. You cannot say. We cannot exactly say it's the last part. Actually, it's maybe in the middle or in the beginning. It's because they are always rotate. First this, first that. You cannot explicitly say in the beginning we solve this or we first solve this or that. But if we want to get a clear understanding, we first solve the transport and then we first solve the pressures and porosities. We get the flow information and then we transfer the components and kinetic species. And then with this information, we solve the local reaction. This is But actually, during the transport, I already use these things to solve other things. So but it's not strictly first this, but it's like a twist handle, yeah. But yeah.
So if you have a species that reacts in both kinetic and equilibrium,
Yes.
is it possible to solve?
So
So if you have a species that reacts in both reactions,
yeah.
kinetic and equilibrium.
Yeah. So this is actually this is the function. The number of the function is the number of the species. If we have nine species, actually we have 9 functions, and with these 9 functions we solve them all together. So this is the function, and we solve them at once, not first this and then this. So we solve them all together in this way. So it's the kinetic reaction and the equilibrium reaction are solved in a coupled way.
I know the question, because the kinetic species,
Yes.
can they be involved in an equilibrium reaction?
No, it will not.
They cannot, or it can.
It will not involve in the equilibrium reaction, but it can affect because because it affects the ionic strength. It can affect the activity.
We have an example of the stoichiometric matrices.
Yeah, this one. Here, for instance,
For instance, the kinetic species, yes,
the calcium.
they always have zeros for the equilibrium reactions.
Yeah, so it doesn't. It will not participate in the reaction, but it will affect because these things will affect the salinity, like the salinity or the ionic strength. It will affect the activity of other things because, for instance, if the water is has a very high concentration of salt, the activity coefficient is changed, so the activity of all the species will be changed. So actually, this one will not participate in the equilibrium reaction directly, but it will affect them because it will change the quality of the liquids indirectly. So that's the reason we solve them all together. We saw like this here is actually is a function of all species. Although in the reaction we only have the activity of the equilibrium species, but we also the species the 9 kinetic species, the activity is also affected by the other 5. They are affected by each other. They are each other. Each species each species. This is the concentration of this species will affect the activity of this species because it will change the ionic strength.
Do you have a model for activity coefficients or you approximate the activities by concentration?
No, we have a very strict like formula, like I don't know the name. They have the function for the ionic strength, for the activity coefficient, for the for the fugacity coefficient. For you have this
Because you have the BU or you have
Then I think you this
the correct pronunciation is to be.
I don't know.
But there are also ways because this is a high salinity, so maybe you have to go to pizza.
And the KF flower, I don't know. There are 3.
Maybe there's something. I don't know.
They have
Pizza.
They have many.
But I don't know what you use. You don't know the name.
Yeah, I know the name. I don't know how to spell. I forget. There are 3 names. Maybe I use debut something, or maybe I just select one because I'm not a chemist. So someone use this one. They say this one is good. So I put a model. But the result is good. So because they have, for instance, they have many models. This one, many people use this one, so I use this one. So.
Okay. And I have a last question from my side. And so, is it in your model, is there only one time step for all of the processes, or will you eventually solve several kinetic reaction steps in, let's say, one flow step, or
No,
all of the equations are solved in the same time step?
in the same time step. I saw one transport and I saw one reaction. I do not, there's no lag. I think you mean we can first solve
The
one
transport, for example, and then reaction steps.
Yeah.
Same.
No, I saw, yeah. The same there, yeah. Maybe for the.
I know someone from the audience. People from the online audience can also say something. So if you want to raise your hand or say something, you can do that. We can hear you. No?
Well, are you considering the porosity variation with time?
Yeah. Yes.
But are you doing like every time? I mean,
Every time.
okay, for example, if you have precipitations or something,
Yeah, consider it all the time. It is including the model, so I think there's a figure, right? This is the porosity change. We do it. It is just one times time that we have this porosity change.
It's not a lot, eh?
Yeah, it's a small. That's the reason.
Less than 1,000.
That's the one. Yeah, one per year. I think this agree with your paper. Yeah. So
Either will have more, higher porosity changes.
So that's the reason. So in the future, if we do some geological carbon sequestration, we can well neglect this porosity change. We do not need to consider, but we need to consider the dissolution because the dissolution might be very important. I didn't put here, but the dissolution is important. It's 20%, but the porosity change is very small, so we can ignore it.
Okay. No more questions? Well, then, thank you.
Thank you very much.